Hello class. Today we're going to learn about electron configuration, or more succinctly, how to do electron configurations. So it turns out that there are three rules that govern the ability to build an electron configuration, and these three rules are the Elfbow Principle, the Pauli Exclusion Principle, and Hunds Rule. Okay? No need to write these down, as we will be going into greater depth in each one of these. So the first one is the Elfbow Principle, and basically all the Elfbow Principle states is that electrons must occupy orbitals of the lowest energy first. Now Elfbow is German, and it means to build up. So it means we're going to build up from the lowest energy level or orbital to a higher energy level or a higher orbital. Okay. What we have here is an Elfbow diagram, and what it shows is the different orbitals and the increasing energy of each orbital. So one of the things to keep in mind is that in every one of these dashes, so I'll draw a line to one of these dashes here, or a line to a dash here, let's say, or let's go to a dash here. Each one of these is pointing to an orbital, and each orbital can only fit 2 electrons, okay? So 2 electrons. So if you were to go up to the F level and count, you'd get 1, let me go back, you'd get 1, 2, 3, 4, 5, 6, 7. There's 7 orbitals. 7, and each one contained 2, which means that the F sublevel can contain 14 electrons. If you go to a D, let's look at the 3D. You got 1, 2, 3, 4, 5 orbitals. Each can contain 2 electrons, so you have 10. Likewise, you only have 1 orbital down here for the S, so there's 2 electrons. And if you were to look at a P, you'd see there's 3 orbitals, for a total of 6 orbitals if you were to complete the P subshell. Now if we take a closer look at this Elfbow diagram, what we see are a couple of things. One thing we see is that the 1s orbital is pretty low energy, and then we see that as the principal quantum number n goes up, for instance 7, we see it's much higher energy. We also start to see things like an s orbital here. 4s is actually slightly lower energy than the 3d orbitals. So we actually have 3d orbitals that appear above the 4s orbitals. In the case of the 4s, this corresponds to potassium and calcium right here. And then the 3d first gets filled with the element scandium. And so you can actually see the order of that. You can see atomic number 19, atomic number 20, and then 21 starts the 3D sublevel, and these are the 4S sublevel. So anyways, keep that in mind, that just because something has a 3 in front of it doesn't mean it's going to automatically appear lower. Okay? And again, we see more instances of that. We see a 4D here that's higher than a 5S, and of course we even see an F sublevel that's quite a bit higher than 2 different 5 and a 6S. So for instance, if we erase these, we see the 4F is higher than the 5, 5S, 5P, or the 6S. Okay? So keep that in mind, that obviously F orbitals are pretty energetic. Now what we're going to learn later on is how to fill electrons. And we draw electrons like this. We'll talk more about that. How we actually fill them up in these orbitals as we build up the Elfbow diagram. Now, we're going to talk about the Pauli Exclusion Principle. And this is essentially about the electron spin quantum number. And the two rules are really simple. An orbital can hold only 2 electrons. So you can only have 2 electrons per orbital, and they must have opposite spin. And we show opposite spin by this type of thing right here, by showing 2 electrons, one with an up and a down. Here, I generally draw them like this, up and down spin. That's the only way they can pair, and it turns out that the up arrow stands for the plus 1/2, and the down arrow stands for a minus 1/2. Okay? So this is basically all the Pauli exclusion principle says is electrons have to have opposite spin, and there can only be 2 electrons per orbital at the most. An orbital can have 1 electron. So for instance, we can, black that out, or it's probably better to do it like this. So for instance, we can have 1 electron, okay, per orbital. That's fine. And believe it or not, orbitals do exist with no electrons. They're just an unfilled or an empty orbital. Now, the last rule is Hunds Rule. And what it says is in a set of orbitals, electrons fill the orbitals in a way that would give maximum number of parallel spins, maximum number of unpaired electrons is the key here. Maximum pair of unpaired electrons. And the analogy I like to use is if you get on a school bus or a city bus or anything like that, generally people will go and sit in the school bus seat by themselves, and the next person will come along and look for the empty seat before pairing up next to somebody. In other words, I want to have more room. I want to, have less energy. Obviously, sitting by yourself in a school bus, you have less energy. If you're sitting next to somebody in a school bus, especially if you're someone like me who's a big person, and you sit next to them, you have to be all sit up straight. You can't beam over, so you have to use more energy to stay in that state where you're paired up with somebody else in the bus seat. Electrons are very similar. Okay, so this is Hunds Rule. So once again, if you have a set of orbitals, and by that they mean like the set of p orbitals, a set of 5d orbitals, a set of 7f orbitals, etc., electrons kind of fill in in an orderly manner, 1 per orbital, until you're to the point where you have to pair up. And so let's talk about that a little bit. We do have one mistake on this slide that I should correct. There should actually be 5 boxes there, not 4, because there's 5 orbitals in the D. So let's talk about the Elfbow diagram for hydrogen. As you can see, we have 1 electron. So this is 1s1. We'll draw it here, 1s1. And you see the 1 electron down there. Now, let's move forward. What if we go to the next one, which is helium? Okay, helium. We see now that we have 2 electrons in this orbital. Now they're opposite spins, and we would say 1s2, like that. Now if we look at something like lithium, what we see is we filled up the 1s orbital, and what is left now is the 3rd electron has to now go into the 2s orbital, so we have a partially filled 2s orbital for lithium. Now we'll move on to the next element, which is beryllium. We see that we now have filled up the 2s orbital completely. We've paired that electron, and we would actually list this electron configuration as 1s2, 2s2. So that would be the electron configuration for beryllium. Now as we move on, our next element is boron, and now we have to go up to the p orbitals, and we will go ahead and fill out the first electron in this p orbital. And again, the electron configuration for boron is 1s2, 2s2, 2p1. Okay? Notice that 2, 2, and 1 add up to 5 electrons, which is how many electrons boron has. Now we've gotten to carbon, and what we can see is we've added a second electron to make a total of 6 electrons into the p orbitals. Notice that I have not paired up the orbitals, paired up the electrons. I've actually put the electron in a separate orbital or box to satisfy Hunds Rule. And again, now our electron configuration is 1s2, 2s2, 2p2. Okay? Now we move on to nitrogen. We have now added all 3 electrons that belong in the 2p sublevel, have each gone into a separate orbital. Notice that their spins are all parallel. In other words, they're all pointing up. This is actually the way they go. There, of course, is nothing to preclude the electrons from all pointing down as well. So that would be another option. They could all go in pointing down, but they either have to all be going in pointing up with the same spin or pointing down with the same spin. But what you can't have, for instance, is something that looks like this in the 3 orbitals, in the 3 separate orbitals. And so again, this is the Elfbow diagram, or the Elfbow diagram for nitrogen, and it's the electron configuration, which is right here, for nitrogen. Now finally we'll skip ahead to fluorine, and we now know that fluorine actually has 9 electrons. We see that 2 of them there in the 1s, 2 of them are in the 2s, and now we have 5 electrons total in the 2p. Notice now that we've actually had to start to pair up electrons. We've actually had to pair them up. And so we see we've made 2 pairs, and we have that 1 lone electron on fluorine. This is generally why fluorine only makes 1 bond usually. And if we wanted to end up making fluorine stable, in other words, make an ion like F-, it would end up adopting the electron configuration of neon, which would be a stable noble gas. And as you can see, why? Because it has a filled second energy level. The second energy level is filled with, of course, 8 electrons, sometimes known as the octet rule. Now at this point, I think it's worthwhile to just take a moment to sort of look at the blocks in the periodic table, because this really helps with electron configurations, and to see where the S block is. The S block is made up of hydrogen and the alkali and alkaline earth metals, and then the D block, which is in the middle. The D block is in the middle, right here. These are the transition metals, okay? And then the P block, we call them the representative P block elements. Many of the elements in the P block are nonmetals. Truth is, if we drew a line right here, these are kind of the nonmetals. These are metals. And the ones in between that are kind of in this region are called the semi-metals, or metalloids. Semi-metals or metalloids. And then finally, the F block is often called the rare earth metals, and they are down below, usually called the lanthanum or the actinide series, and they're down here. Okay? And so, and again, remember, these guys actually kind of squeeze in right between the 6s and the 5d, and the 5f squeezes in between the 7s and the 6d. Okay? So maybe I can draw that a little bit better. The 4f will squeeze in right there, and the 5f actually squeezes in right there between those two. Okay? So anyways, probably one of the biggest issues you'll notice is that we actually go from 4s to a 3d. So we have this phase shift going on between the 6s, 5d, 6d. So that's something to keep in mind. And then there's a double with the 4f's and the 5f's. They're a little out of kilter. They're all the way down by the 6 and the 7. But one thing that is nice is that the P levels are on the same as the S levels in all cases. Okay, so that should make it easier. This is definitely something that you want to be able to just look at the periodic table and be able to identify these blocks, identify, 5D, be able to look down and identify that it starts with lanthanum, hafnium, tantalum, tungsten, these types of things. Okay. And again, I think it's worth mentioning, I talk this to my regular chem kids all the time. It's definitely worth mentioning that, we know there's an one s orbital and it contains 2 electrons. And if you did the counting, what you would see is if you look at any one of the s blocks, you'll see 1, 2, 1, 2, to show that there's only one orbital with 2 electrons. If you go over to the p, there's 3 p orbitals, and each one contains 2 electrons. 1, 2, 3, 4, 5, 6. That's why there's 6 elements in that row. And again, obviously, the D can contain 5 orbitals, which means 10 electrons total. If you count, you get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And trust me, there is 14 boxes down in each of these rows as well. So here's a formal slide showing what's called standard notation of fluorine. Number of electrons in the sublevel are the red superscripts, 2, 2, and 5, so that adds up to 9. And that's how many electrons fluorine has total. The blue S's and P's are the sublevels or the sub-energy levels, and these are actually, of course, as we know, the word sublevel and orbital are kind of one and the same. So those are the orbitals, and then the numbers on the ends are simply telling you which period it's in. 1, 2, 3, 4, 5, 6, 7, which is the main energy level numbers. These are the Bohr orbit numbers from originally. This is again usually n equals 1 through 7 potentially. And so this is just what is known as standard notation. And if you do it in electron configuration, in standard notation, you always have to start out at hydrogen with 1s2, and you just start rattling them off, going down the periodic table to the element that you are searching for. Now, once students do a little bit of shorthand notation, it gets a little crazy, and they say, wow, I have to write so many symbols, like, what if I do something like, let's pick an element like strontium, okay? And so we're going to pick strontium. So SR. The truth of it is you could start writing 1s2, 2s2, and just keep on going along, and you would get tired pretty quickly. So we've developed a shorthand notation, okay, that uses the last noble gas that is located in the periodic table right before the element, and you would simply write the symbol of the noble gas in brackets. So what I've shown here is the 2 different electron configurations that you can use for strontium, which is SR. Above is the standard notation. It's hard to read it, but it goes 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2. Let me double check to see if I got that right again. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Then it goes to scandium, which is 3d10. And then we're at gallium. So we start at 4p6, which takes us to krypton. And then finally 5s2 takes us to strontium. If you want to do shorthand, we just go back to the last noble gas, which is krypton, put it in brackets, and then write 5s2. Okay? And so on tests and problems, we will actually ask you to make that distinction. What's the difference between standard or shorthand, vice versa? As we move along, we'll get away from standard and get more towards shorthand. And that will end this lecture on electron configuration. Hopefully you now have a better idea of how to get electron configurations and how electrons will actually go into orbitals and whatnot and pair up, and how they don't pair or pair and things like of that nature. Thank you very much, and I hope you have a good rest of the day.